In this lecture, we will talk about the Kelvin's circulation theorem. The Kelvin circulation theorem can be seen theorem where we are interested in know the rate change of circulation. So let's write this down. In other words, lambda being the circulation, we are interested in finding what is this. Okay, this is where Kelvin's theorem helps us. So our goal is to see how the circulation is going to vary as you move from one loop to another loop. If you remember, what we really have is we got the flow, right? And then I have one circulation loop and I can have another circulation loop. What happens from one loop to another loop is what I am really interested here. Okay, let's suppose this is the loop at time t, and this is a loop at time t plus delta t. Okay, so as a loop, I'm moving from this point to this point. This is what it's going to look like. So the goal that we are looking for is to determine. We want to determine how the circulation around the loop varies as the loop moves with the flow. Okay, I want to keep this. This is not two separate loops. Okay, this is the same loop. It just moved with the flow. Okay, so now the loop was here, and as the fluid keeps flowing, now the new loop is at this location, and that's what we are trying to do. Okay. Okay, so first of all, if we go back as a simple review, you remember that we define circulation as follows, right? Lambda is equal to, and we are going to use always counterclockwise. That's our convention, d of s. And then we can see that the rate of change of circulation will be the following. d lambda dt is going to equal to rate change of the circulation times d dt, or I should write it like this just for completeness, dtt v dot ds. And since it's a closed loop, this is really a property of integrals, is the same as taking the total derivative of this term. Okay, so let's go ahead and work with these terms. Let's work with this term separately, and then we'll put it back. So d dt of velocity dot ds, the line integral, will be nothing else than d dt using the chain rule okay. So what we know is let's suppose we have a fluid, okay, and the flow around the fluid does the following. So we can call this distance S1, call this distance S2, call this distance S3. Okay, so I went from this position to this position, so this is time t, this is time t plus delta t. So if I go to t dt ds times dt, that will give me minus the velocity respect to time. Okay, this will be at location S1 plus ds. This is S2 because I'm coming here is minus because I'm taking positive this direction. Going here, and then this will be plus v dt dt. This will be my position as 3. Okay? And just remember, this is negative. Once again, this will be negative because my flow is going in this direction. Okay? So all my flow is going in this direction. So this is going in the opposite direction. That's why this is negative. Okay, so now we can go ahead and simplify that. If you realize that I have this term and I have this term that can cancel out, and then I have a ds here, I have a ds there, then if I simplify, you can show that the term that you get is the following: dv. So in other words, then the enclosed integral will be nothing else than the velocity dt ds is going to equal to integral of the velocity, and this is nothing else than my d. This is nothing else than, if you realize, uh, the volume, right? So if you look at this, this is what you will get. Now volume, velocity. So this is the velocity. In other words, the closed integral over the loop would be d v squared over 2. And since this is a scalar, this is basically is going to give me equal to 0. Okay, the integral around the loop will be 0, and we know that. Okay, so if I have any loop, doesn't matter what the loop looks like, and I start and end at the same point, that enclosed integral will be of whatever is going to actually equal to 0. That's by definition. That's the way it should be. Okay, so with that said, we go back to our term. So we found that the integral, this is 0. So I'm basically left only with this integral now. So the integral would be, so then the rate change of circulation will simplify ddtv dt of velocity and the dot product with the distance simplifies to this dv dt dot ds. Now we have seen this term in the past, so let's go and expand on that term and let's see what happens. Okay, now from your momentum equations, this was Newton's second law, if you would. We found and we derived this uh, previously in the course. Gives you rho plus your V, and this is viscous forces. Okay. So if I take this and I bring it inside here, and I add the integral, I can find that my integral actually now becomes this is equal to the integral of f dot ds minus the integral of delta p respect to rho dot ds plus the integral of v of f dot ds, okay, over the same enclosed area. Okay, so let's go and see what happens with each one of these terms. Okay, so this is term number 1. This is going to be term number 2, and this will be term number 3. And this is going to enclose the Kelvin's theorem. Okay, so the Kelvin's theorem states the following. Okay, states the following. The circulation around a fluid loop may change only as a consequence of the following. So number 1 is the consequence of this term. Okay, there are 3 terms, and those are the 3 things that we will talk. The first one is the body force. The body force torque. Okay, what is the torque generated because of the body force, and the body force around the enclosed loop is going to have 2 values. Okay, first is going to equal to 0 if F is irrotational. So many times, irrotational. Many times we have no information about the body force, if it's rotational or not. What you will do is just assume this, because this is the conservative case, okay? Since this is conservative, this one is acceptable. The second case that you have is when this is not equal to 0, and this is mainly like the case of a magnetic field, as for example. The magnetic field, it is a rotational body force. Okay, so that solves the first case. The second, the second term that we are looking here is the pressure force torque, and that has to do with this term, delta P over rho dot ds. Okay, and this term is equal to 0 if your density is constant, or if your pressure is a function of the density. Okay, so it's not going to equal to 0 if density changes. Okay, and this is also known as the isotropic case. Okay, now the third term that we have is the viscous force torque. This is actually going to equal to, let's put this way, this is 0 only outside the viscous region. Okay, so if we put everything back together now using your Kelvin's theorem, then we have the following. If we assume rho is constant and F is equal to delta U and flow is irrotational, then we're going to have the following. We're going to have this minus P over rho. This is going to equal to delta U minus delta P over rho. And this is the same as delta U minus delta P over rho. So the term B dot ds respect to time is going to give you delta U minus delta rho pressure over rho dot ds. Okay, and this term right here, if you would, if you realize this is also the gradient is going to have partial of x I plus partial of y j plus partial of z k plus, and then this, and then you have all these constants, right? Let's call this constants beta for a moment. Call this beta, 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 and this dot product is nothing else than the product of dx of I, dy of j, dz of k. So if you look at this, this is dot product of this, and you can see how this and this cancel out, right? And this cancel out, and this cancel out. So at the end of the day, I can say this is the same as the differential of this minus delta P over rho. It gives me the same. So what I am trying to say is then this integral right here, okay, this last integral that was remaining, so we know that this was equal to this. Let me check this to the next page. Okay, so now what we can say is we know that this is actually equal to du minus p over rho. I have a small mistake here. This gradient doesn't go here because I factored this out, as you can see. It was factored out, so this rho doesn't, that delta doesn't go there. So over a loop, this is actually going to be 0, okay? Because if I take the loop of the A, let's say, and I'm going from A to 1 minus A to 2, that's going to give me 0 because over the loop, that's actually 0. So that's why this is actually going to give me 0. Okay? So basically, in other words, what Kelvin's theorem is stating is the following. I can express the Kelvin's theorem in the following expression. So your Kelvin's consequence under the assumptions that we made tells me the following, that your circulation, we know this, right? By Stokes' theorem, we discussed this in our previous lecture, and this gives you S dot N D of S. So what I am saying is that you have the circulation respect to time is going to actually equal to dt of the double integral of rho of this is a vector dot n ds as well. And under the consequences that we did, this can be equal to 0 or it cannot be 0 because of the consequence of this side. And it's 0 whenever I take the following assumptions. Right? We make a couple of assumptions, and this will be 0 if rho is constant, if it's possible to express your body force as a gradient of u is a quantity, and the flow is irrotational. So this is the end of Kelvin's circulation theorem.